Just a quick overview of where we're at in the class. So the Sandler book has up through chapter 6 is basically looking at the behavior of real fluids, single component, single phase. Right, chapter 6 is the one where we derive all of those expressions based on how does enthalpy change, how does entropy change, and the likes there. Using an equation of state or real data, right? Basically, it's a dp, dt type stuff. Chapter 7 is where it introduces the fundamentals of phase changes, and that's where we talked about the definition of fugacity, how we can use a cubic equation of state in order to calculate phase changes. Chapter 8 is where we're at right now. This is looking at the principles and fundamentals of multi-component systems. So essentially defining things like the partial molar property, right? This little guy here. Partial. This is defined based on B. Today, we're going to be closing up chapter 8, which is the fundamental basic principles of multi-component systems. And we'll move on to chapter 9 either at the end of today's lecture or on Wednesday. Chapter 9 is where we actually start calculating these properties for actual mixtures and systems. So starting off obviously with an ideal gas mixture, how do we calculate the fugacity of an ideal gas? Then how do we calculate the fugacity of a real fluid mixture? Then eventually, chapter 10 is where a lot of Thermo 2 classes would start off. That's something like Raoult's law. Multi-component, multi-phase systems. So I know it's a long path to get to sort of the application, but the hope is that if we ever go back and kind of revisit everything, it'll be a lot quicker to kind of go to the point we're at right now. So when I watch sort of video lectures, not of myself, but of other ones, just to try and get a different perspective of how people are teaching topics, I always watch them at like 2x speed. So if we were to go through all of the derivations at 2x speed, to get to this point right here, it'd probably only be like an hour and a half worth of work or so. But it really gives a good, clear foundation for how we actually get to this point in thermodynamics. So hopefully it seems a little less arbitrary than it has been in a typical undergraduate course. So just a quick overview, just so we're on the same page. When we're talking about mixtures, so we write theta here, but this could be volume, this could be enthalpy, this could be internal energy, right? It could be a number of things. So we're just writing very generally. When we have theta with an underbar, no subscripts, this is going to be the total mixture property or the total property of a pure component. It's going to be context-based. If it's a pure system, then there's no reason to put a subscript, obviously, right? If we have theta underbar with a subscript, pure component I property. So for example, if we have a mixture of water and ethanol, this could be the density or the volume of water, the density of ethanol. When we mix them together, we will get the total property value here. We can have a change of the property in mixing, so sometimes I'll write mix down here, sometimes I'll just leave it delta. This is going to be the difference between the partial molar property in the mixture minus the property pure. And we can rewrite this a number of different ways. This one's pretty convenient. Or we can also write this, the delta of mixing, as the total mixture property minus a weighted summation of the pure properties. So this is going to be our ideal mixture, mole fraction, times by the pure properties. Subtract that from the actual system mixture properties. So this is going to be a function of temperature, pressure, and composition. This is going to be a function of only temperature and pressure. And so that's kind of the notation and nomenclature that we covered last week in class. But what we're going to be doing is how do we calculate all of this here is how do we actually evaluate these types of expressions. Our ultimate goal is on Wednesday, we're going to be defining the partial fugacity, and this is going to be our gateway to equilibrium for multi-component, multi-phase systems. Sort of in the same way we used fugacity to calculate the phase change for a single component, which is what your homework is going to be solving on question 7. The critical point of carbon dioxide is 304 Kelvin, 78.2 atmosphere. Initially I have some composition, but basically what I'm going to be asking you is to solve for the vapor pressure of CO2 at a given temperature using an equation of state. Then what you'll be doing on homework 3 is you'll be taking that and you'll be generating an entire phase diagram of CO2. Additionally, the one problem that I say you'll probably spend the most time on in this homework is number 3. You'll be building your own saturated enthalpy and entropy table from ethanol using heat capacity data there as well. So those 2 problems are going to be probably your most extensive ones that spend the most time on. All right, so a few loose ends to tie up before we transition on to actual expressions where we're going to be evaluating the partial fugacity. Yes, question?
What's the theta I over bar?
Theta I over bar is the partial molar property. So this is effectively, you can kind of think of it as how does this fluid behave in the mixture relative to how it behaves by itself. So in this case here, this corresponds to how fluid I behaves in the mixture. The underbar is pure. So in the mixture, it's a function of temperature, pressure, and composition. As a pure species, it's only a function of temperature and pressure. But this here is effectively going to be related to the partial molar Gibbs, which is then related to its equilibrium. That's the reason why we're going to go through this whole procedure here. The most important. All right, so Gibbs phase rule. We're going to finish off our discussion of this, looking at multi-component and multi-phase. So, if we look at, let's see, one component, one phase, this gives us 2 degrees of freedom, temperature and pressure. So if we fix temperature and pressure, we understand everything else about the system. Density, internal energy, so on and so forth. If we do multi-phase, one component, this is something we talked about, I think maybe last week. This gives us to 3 minus p degrees of freedom. So in the case of, let's say, vapor-liquid equilibrium, that's 2 phases. 3 minus 2 is 1, which means that if we fix the temperature, the vapor pressure is locked. If we fix the pressure, then the temperature is locked. Right? So in our case with atmospheric pressure, which is what we all are used to, every fluid boils at a set temperature. That's our 1 degree of freedom. Now, if we talk about multi-component and multi-phase, what we have is that we need 2 degrees of freedom plus C minus 1 per phase. Now let's walk through this really quickly. 2 Yeah. So 2 defines the temperature and pressure for each component. The C minus 1 defines the composition. So for example, this would be temperature and pressure, and this defines the composition. Oh, sorry, this is multi-component single phase. Multi-component one phase, multi-component multi-phase, multi-component one phase. So, the last one, multi-component plus multi-phase. This is equal to C plus 1, which is equal to 2 plus C minus 1. C minus 1. So, same approach here. So, if we have 2 degrees of freedom, that gives us the temperature and pressure, that defines the properties for every component in the multi-phase multi-component mixture. We need an additional C minus 1 piece of information to describe as the composition. So in the case of, let's say, a 50-50 mixture, we just need the mole fraction, right? So you need only the mole fraction of one of the components, because you can do, x of A plus x of B is equal to 1. So that describes all the information we need to have for a multi-component single-phase system. Then for every single one of those phases, we have to have the same piece of information. Then we have to determine our number of dependent equations. So we're going to go through the same list as before. So we have thermal equilibrium. T phase 1 equals T of phase 2, dot, 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 dot. This gives us P minus 1 expressions. We have mechanical. P of 1 is equal to P of 2, P minus 1. And then for chemical equilibrium, we have a little bit different. In this case, for component I, we have the partial Gibbs of phase 1 is equal to the partial Gibbs of phase 2. So we have this for each number of phases minus 1. For component J, we have the partial Gibbs of species J is equivalent across all of the phases. So then what we get for the number of dependent equations, so we have degrees of freedom is equal to the number of phases times by C minus 1, which is what we get for a single component, minus our dependent equations. So in which case here, temperature and pressure are constant across all phases. So we have 2 times number of phases minus 1. And then here, this is dependent on the number of components we have in the system, plus the number of components times by P minus 1. So if we do the algebra, what we get is that the degrees of freedom for the Gibbs phase rule is the value that or the equation that everyone should be at least somewhat familiar with for the Gibbs phase rule for how many degrees of freedom that we have to actually have across the whole system. Everyone on the same page. Now this tells us tells us the number of phases in the state of the system, right? Is it a solid, is it a liquid, is it gas, is it two-phase? But it doesn't say how much of each phase we have. In order to piece together that information, we need additional information like what is the total enthalpy of the system? What is the total specific volume of the system? What is the total entropy of the system? Right? Because these are going to be weighted summations of each phase's information. Right? So if I have a vapor-liquid equilibrium system, right? Let's say we're at the bubble point where you have 99.99% liquid and just a teeny little bubble in the system. That means that the enthalpy and the specific volume and the entropy of the system is going to be that of, let's say, pure liquid. You could also have the same temperature and pressure situation and have 100% vapor with just a teeny, teeny, teeny little bubble in the system, in which case these values would all be that for the vapor phase. If you had a 50-50 mixture, it would be an average between those two. So we need additional pieces of information to figure out how much of each phase we have in the system. Okay. The next one is a very famous equation. Who here has heard of the Gibbs-Duhem equation? Do you guys remember what it is?
No, off the top of my head. Something that Brennan showed me on a whiteboard the other day.
Yeah.
That's what it is.
So the Gibbs-Duhem equation is a very critical and necessary piece of information for multi-component phase equilibrium or multi-component mixtures for thermodynamics. You don't actually use it very much in solving problems, but it is a critical piece of information that is necessary for deriving all the expressions that we're going to be using. What it is a thermodynamic consistency relationship. So I'll explain what I mean by that. So another consistency relationship is basically what it's saying is this is kind of a definition that we can't violate. So if we do a mass consistency relationship, what I mean by that is if we take the summation of all of the mass fractions or mole fractions of the system, it has to be equal to 1. This is really just a definition. Right? This is a consequence of how we define what mass fraction is. Based on defining mass fraction or mole fraction as the number of moles of species I over the total number of moles, or we can write that as number of moles of species I divided by the summation of all of them, right? This is the definition of the mole fraction, let's say, for example. In a non-reacting system, mole fractions and mass fractions can kind of be used interchangeably. They're not the same value, but the concept is the same. If we define mole fraction this way, then this relationship must be true always, all the time, under every circumstance, no matter what. The Gibbs-Duhem equation is exploring the same concept, but evaluating the consequences of our definition of the partial molar properties. So because we have arbitrarily defined the partial molar properties, the Gibbs-Duhem equation is an additional relationship that says, okay, now that we've defined it, what has to be true? What rules can we not violate with respect to multi-component mixtures? That is what the Gibbs-Duhem equation is. Right, so all it is a mathematical consequence based on how we've defined the partial molar property. Number of moles of J is not equal. Holding constant everything that is not I. Okay. So we're holding temperature constant, pressure constant, and everything else except the number of moles of species I is being held constant. So all we're doing is we're taking a bucket of material. There's I, J, K compounds, and we're adding in a little bit of I to the system at constant temperature pressure. And we are measuring the total mixture property. That's the mathematical definition, or sort of physical definition of what we're doing with the partial molar property. I've got a bucket of a multi-component mixture. I'm adding a little bit of one species, and I'm holding everything else constant. That's all I'm changing. So again, remember that this is just sort of a matter of convenience. All of the variables are always on constant. So this nj not equal to ni, or xj not equal to xi, I don't know how many more of those I got in me. So I might be truncating that for the mixture. All right, so that is what we're trying to do. What are the consequences of that definition, and what are the consistency relationships that have to be derived as a result of it? Without the Gibbs-Duhem equation, we cannot simplify a lot of our equations that we'll be talking about over the next couple of days. They will be too complicated if we assume that every variable is independent. But what the Gibbs-Duhem equation will do is that in the case of x of A plus x of B is equal to 1, mole fraction of A plus the mole fraction of B is equal to 1, right? In the case of the Gibbs-Duhem, we're going to have similar relationships like this, but with respect to partial molar properties. And so without the Gibbs-Duhem, we're not going to be able to simplify them to actually usable equations. So we're going to start off all of our derivatives, all of our derivations like we always do. So we're going to expand the total mixture property with respect to temperature, pressure, and the composition of the system. So this is the total derivative of the mixture property. So this is the total derivative. What are all of the properties that will influence, let's say, the specific volume of the system? Right, so we can think of this as, what are all the properties that are changing the molar volume? But in this case, we're going to expand it with respect to the composition as well. So just the same thing we've done normally. This, we'll notice here, this is exactly the definition of the partial molar property for species I. We'll rewrite this a little bit. Since n is being held constant in each of these scenarios, we can pull out this. Oops, sorry. It's not there. Okay. So what we're also going to do is we're just going to use the product rule on this expression right here, which is equivalent to what we started off with, in which case this is equal to the Since we have an arbitrary number of n components, then the product rule will be summations. So we have to take the partial molar property derivative. Sorry, hold on. I skipped a step that I need to highlight. Where's my eraser? Actually, I don't need this. It'll be clarified if I show this. Sorry, there we go. So, all right, let me just rewrite that. Let me just start this one over again. The outcome is the same, but let me just make it clear why we're doing it this way. So we want to evaluate how is the total system property changing with respect to all the variables that can be present in the system. This is the same thing as if we substitute in how we can calculate this using partial molar properties. All right. So now when we expand the total derivative here, we're expanding it, right? Everything is a property of everything else, so that means we have a summation here. That means we hold this one constant, take all these derivatives, take all these derivatives, hold that one constant, right? Just the standard product rule. So in this case here, all right, makes more sense there. So what we're going to do now, we'll notice that there's a lot of similarities associated with these equations. The left-hand side is equivalent for both of them. We see here that we have an expression with respect to n, and this one here with respect to n. But ultimately, we're trying to derive a thermodynamic consistency relationship with respect to the partial molar property. Right? That's what we're trying to do here. We're trying to figure out how do all the partial molar properties have to be related to one another in order for all these equations to be consistent. So the convention here is I will call this equation A, I will call this equation B, and we will do B, let's subtract this. So we're taking B minus A, and that gets us to the Gibbs-Duhem equation. In which case that gives us 0 is equal to all right. A few more steps before we simplify it down. Just to clarify, the left-hand sides cancel out. This expression here cancels with this expression there, and then we have these become negatives because we're subtracting that equation. If we divide the whole thing by n, so we'll do two steps. We're going to divide this equation by the number of moles in the system. We're going to hold temperature and pressure constant. The reason for that purpose is because when we're dealing with multi-component mixtures, it's easier to mix things isothermally. So there's only one variable changing, which is the composition of the system. That gets us to the generalized Gibbs-Duhem equation that we care about, written either in two ways. So, what the Gibbs-Duhem equation is telling us is that adding up all of the partial molar properties in this sort of a convoluted mathematical way, we'll rework this in a bit more convenient way in just a second. But what this is basically saying is that I cannot independently verify any of my partial molar properties without modifying the partial molar properties of the other things in the system. This is 100% equivalent to looking at the mole fractions. I cannot vary the mole fraction of species A in a mixture without modifying the mole fraction of species B. What this also tells us sort of fundamentally is that if I create a mixture, I cannot say that one single component is responsible for the property changes. The mixture itself is the property itself. So if I add, let's say, sulfuric acid and water together, the hydrogen will dissociate from the sulfuric acid. It'll go on to the water. That'll lower the energy of the system, and it'll give off energy, and that's why you have an exothermic heat of solution properties with something like sulfuric acid and water. But we cannot say that that exothermic process is because the sulfuric acid gives up the hydrogen, or it's because the hydrogen is accepted by the water to make an H3O+. That is the consistency relationship that the Gibbs-Duhem equation communicates. That based on the definition of the partial molar property, right, which is going to be related to the partial fugacity, which is related to the partial Gibbs, we cannot independently move anything separately. What that also tells us is there's a big consequence now. That when we have a multi-component, multi-phase system, we have to solve it all at the same time. We cannot break it down into individual steps, which means that we have to independently, so if I have a multi-component, multi-phase vapor-liquid system, which is going to be the lion's share of what we care about, our objective is that the partial Gibbs of phase 1 of species A is equal to the partial Gibbs of phase 2 of species A. The partial Gibbs of species B in phase 1 is equal to the partial Gibbs of species B in phase 2. In addition, the temperature of phase 1 is equal to the temperature of phase 2. The pressure of phase 1 is equal to the pressure of phase 2. Because of the Gibbs-Duhem equation, what is happening here is that a particle of A may move into the liquid phase. What's happening there is that I'm changing the composition of the vapor phase, and I'm changing the composition of the liquid phase. So as I change the composition, so I'm moving one molecule from vapor to liquid, I'm changing the partial Gibbs of A, and I'm changing the partial Gibbs of B for both phases. So because of the Gibbs-Duhem, that means I have to solve this entire system in one go. There is only one solution where this is going to be valid. I cannot break it down into smaller steps. And so my equilibrium solution becomes one big, multivariable, nonlinear solution problem. Right? So I cannot solve the phase equilibrium for A and then move on to B because they are all connected together. Does that make at least sort of intuitive sense of why we have to have it? This right here means nothing to me because I cannot independently change the partial molar property. So while this equation is conceptually extremely useful and it comes up in derivations a lot, it is not something that is particularly useful for you and I to have. So there's something that we can do to modify it. But the consequences of the Gibbs-Duhem are very significant in terms of how we have to think about all of multi-component thermodynamics. But once the concept sits in that everything has to be changed and modified simultaneously, the actual application of the equation is something that is not done particularly often, except for when we're deriving our first set of variables. So let me move on to the next section where we will rework it in somewhat of a more convenient manner. So what we're going to do having the partial molar property of species I as our independent variable that we can modify and change, right? So things like dP, right? That makes sense. I can change the pressure. How do I change the pressure? At what rate? That's trivial. I increase the pressure, I decrease the pressure. Same thing with dT. I increase the temperature, I decrease the temperature. Trivial, trivial. I have no idea how a multi-component, multi-phase thermodynamic system is going to behave when I change any properties like temperature, pressure, or composition. If I could, thermodynamics would be a whole lot easier. So instead, I don't want to have anything as an independent variable of my very complicated, very convoluted partial molar property. So instead, what I would like to have is changing the mole fraction. Right? If I want to change the mole fraction of a mixture, I just add a little bit more of component 1. I just take away a little bit of component 1. Add a little bit more of component 2. Right? All of these are means that I can change this. So what we want to do is rework the Gibbs-Duhem equation out of this form and into a form that has the mole fraction where we can actually think about it conceptually. So what we're going to do here is I'm not actually going to go through the math. We're going to take exactly the same approach, but instead of expanding it with respect to temperature, pressure, and number of moles, we're going to expand it with respect to temperature, pressure, and mole fraction. And skipping over a little bit of the mathematics, we will get that the Gibbs-Duhem equation reduces to something that is not particularly visually appealing. Another wonderful form of the Gibbs-Duhem equation. However, for our purposes, we're not going to be dealing with this equation for much more than 2 components, otherwise it gets out of control very quickly. If we have c equals 2 and we are very diligent in keeping track of our I and j indices, we will get this expression here. These are total triples, actually. Oh, partials, sorry. This is the quote-unquote useful form. Uses of the Gibbs-Duhem equation. Number 1, it's going to be really helpful in derivations for what we are trying to calculate over the next couple of class periods. Number 2, if you have calculated partial properties based on experiments that we're going to be using to benchmark and optimize equations of state, the Gibbs-Duhem equation is a available to double check your calculations. So the first standard test that someone would do if they're submitting their data to a thermodynamic journal is to verify that their measurements are consistent with the Gibbs-Duhem equation. If not, universally something is wrong. Either something is wrong with the analysis, the measurement, the experimental design, whatever. The third thing is if you're very confident, you could use it to reduce the total number of experiments you have to do. So these are the main uses of the Gibbs-Duhem equation. But the best way to think about it is that it is more or less just a consistency relationship. Now, the reason why we need a consistency relationship is because, as it turns out, it is very difficult sometimes to make experimental measurements on multi-component systems, particularly if there's multiple phases going on. Here's the reason why. If I'm measuring some experimental property, this is why thermodynamics is still studied and it is still challenging. I'm looking at the mixture properties of some system. In this case, we like to draw kind of the axes in the middle. Now we can think of this as either, let's say, the heat of mixing, the volume change of mixing. So if this is the heat of mixing, and I have a measurement up here, is that an endothermic or an exothermic process?
Is that 0, the horizontal line?
Yeah, that's 0, sorry. This is 0, this is positive, this is negative. So if I mix two things together, and I have a positive change in mixing, is that endothermic or exothermic? Why is it endothermic? This is at a constant temperature and pressure.
So if the energy of the system increased, then it brought it in from outside, from the surroundings?
Correct. So if we have a mixture well, we can define our reference conditions. So we'll define our reference conditions at the temperature and pressure that we are mixing the system at. Okay? So this is 0 enthalpy. Then if I go through a mixing process, I have two outcomes. My enthalpy of the system can increase, and the enthalpy of my system can decrease. So what happens is if my enthalpy of the system increases, that means that my system has more energy stored per molecule. Since that energy can't come from anywhere, the only place available that it can come from is from the kinetic energy and the movement of those molecules themselves. So it sucks some energy out of the movement of the molecules and it puts it into the non-ideal structural behavior of the fluid itself. Does that make sense? Whereas in the case of lower energy, like let's say a sulfuric acid and water mixture, having the hydrogen leave the sulfuric acid and go onto water is a lower energy state. Which means now that we have a surplus of extra energy now available in the system. The only way that the molecules know how to store that energy is by moving more quickly. So it's a little bit quickly counterintuitive. Negative delta H's of mixing are exothermic, positive are endothermic. Same thing, another way of thinking about it, but I always like to think about, if you think about how the energy is actually stored, you know, when it's a higher energy state, it's actually colder because that's where all the energy has to come from. So if we're doing calorimetry measurements, we may have data points that look like this. To me, that doesn't seem catastrophic. To thermodynamics, this is catastrophic. Because if I were to then, let's say, just connect the dots, this is very, very, very bad. Because we know that due to the stability criteria of the universe, entropy always must be concave. Gibbs must always be convex. So if I'm making a really important thermodynamic measurement that I'm going to be using to benchmark my multi-phase, multi-component systems, The consequence of these is that temperature and pressure always have to have, pressure and volume always have to have an inverse relationship, which is how we use a cubic equation of state to calculate vapor pressure. This region here is unstable because you have a positive slope. So when we're dealing with real thermodynamic experimental data, we see this as a positive slope, a negative slope, a positive slope, a negative slope, right? Having these inflection point changes in thermodata will give you vastly different conclusions for how you should actually be modeling it. So in thermodynamic data, we don't ever actually want to use the real measurements because the real measurements have noise, and noise introduces uncertainty. Uncertainty in experiments is amplified when you take a partial derivative. In experiments, integration always smooths out error. Derivatives always amplify error. So what we'd want to do is to have a function that matches the curvature roughly, but doesn't get bogged down by the experimental noise. That's why we want to make sure that our fits are consistent with thermodynamic consistency relationships, because you may have hundreds of millions of dollars based on a separation procedure for a chemical plant that really, really needs to have accurate thermodynamic data. So that's why it's a really important consistency check, and it's used all the time. So what is done instead is we choose certain polynomials that seem to fit the data well, that don't necessarily introduce artifacts of curvature that are going to influence our understanding or our perception of how the phase equilibrium is going to change. So one such polynomial that is very popular is a Redlich-Kister polynomial. It matches a couple of really key characteristics, namely that in a composition of zero of either component, that your property change upon mixing is zero, which has to be true, right? I can't have a delta H of mixing for pure water. It doesn't make any sense. So if I'm trying to fit mixing properties, this polynomial form is a really good one, and there's lots of others. This is one of the more popular ones. Right, in this case, I is not the number of components, it's the number of terms in the polynomial fit that we use. But because the leads with x1 and x2, that means that at any time you either have x1 or x2 equal to 0. So in this case, we write this as a function of x1. So here we have x1 equals 0. Here we have x2 equals 0. At any of those end limiting points, this goes to 0, which means it's a good fit. This is a polynomial, so you have a coefficient and the difference of the two raised to the power. This is a standard fit that is used to fit thermodynamic data, which you will then want to take your fits and confirm using the Gibbs-Duhem equation that you're actually going to have consistent data that is not violating basically the principles of thermodynamics. Okay. So this is one of the things that makes thermodynamics very challenging, particularly if you're trying to model the behavior of a dilute system. Oil and water, for example. And that's something I brought up in the past with respect to reservoir simulations. If you have a multi-phase reservoir with oil and water, or oil, water, and gas, just a small amount of water in the system can massively change the flow characteristics of how that oil or the water migrates through the reservoir. So being able to sort of categorize, measure data, getting accurate equations of state is something that is non-trivial to do, and that's why we still basically study and focus thermodynamics. Right? The basic mathematical principles of thermo have been established for 200 years or so, but the problems that we're trying to solve with it are really challenging. And so these are the tools that we have available. So that basically concludes all of the foundational principles of thermodynamics. The only additional things that we have left to do before we get to solving these real problems is we're going to define the partial molar fugacity, the partial fugacity, not partial molar, partial fugacity, and then we're going to simplify that expression based on whether or not the system is an ideal gas, a real fluid, a liquid, and whatever the case is. So from that point onwards, it's just going to be solving real system, multi-component, multi-phase equilibrium, after we just define a few more terms and then we figure out how to simplify it. All right. Tomorrow, 12 to 1:30? Or is it 1 to 2:30? 1 to 2:30 help session. I'll send out an email. Please do look at the homework as soon as possible so we can have lots of good question and answer sessions. All right, thanks.